So my name is Akomeah, and it's a privilege to be joining you for this 15th webinar. So I have a background in civil engineering, specializing in water resources engineering and management. So my area of specialty is with tools for long-term management of catchment. And so over the course of my professional life, I've been developing integrated tools, environmental models to be precise, coupling them to solve some of the world's problems with respect to long-term sustainability of environmental systems. And this afternoon, back in Ghana, I'm very happy to share with you some of the strategies that we can use to solve some of these environmental problems. So I'll share my screen and then we can start off. Please let me know if you can see the screen.
Yes, we can see your screen.
Okay, awesome. So when you look into the scientific literature, it's been established that Earth's life support systems are on the verge of collapse, what they call tipping points. And unless governments around the world or every one of us kind of intervene in one way or the other to reverse some of the processes that are still sustaining this collapse, we are on the verge of losing some of the benefits that we gain from our environment. And I'm very happy to share with you one way of doing that in the area of floodplain management with a policy tool to ensure that such a strategy can be implemented successfully and the benefits that we are hoping to get realized. And so we will go through together what a floodplain is and some fundamental processes. If you put on one lens, looking at a floodplain, we might lose sight of so many dynamics within the plane. And so you can put on the lens of hydrologist. You only capture just one component of it. Geomorphologist would also capture one side of it, or an ecologist. But we look at it from the angle of a system and systems dynamics. We can't handle the issues within that system appropriately. Then, secondly, we will look at some of the environmental benefits that are derived from such a system. Then we will take a step back and consider how we've managed the system in the past, but most jurisdictions around the world are still holding on to such paradigm and managing the system the old way. Meanwhile, there is ample evidence within the scientific literature of how there are unintended consequences that are coming from such management approach. Then finally, we would come to how we can sustainably manage the floodplain, use it wisely, and leave the benefits for us and future generations with a policy arm. And so floodplain or floodplains are areas within the natural landscape that are shaped and sustained by water courses. And water courses here refer to rivers, lakes, wetlands, seas, you name it. And because they are situated beside those water courses, there's an exchange of flow, sediments, nutrients, and organisms. And so the hydrology of a river, and from this point on, I'll just concentrate on the watercourse as a river and leaving off the rest. So the hydrology of a river affects the floodplain's geomorphology. That is simply the sediments and particulate substrates adjacent to the floodplain. And so together with such a landform and the river, a substrate is created that supports various ecosystem processes. So when you take the hydrology of a river, the flow regime influences the flow within the floodplain in so many ways. So when we talk about the flow regime, we are referring to the magnitude of flow, the duration, frequency, time, and residence time. All those characterizes the flow regime of a river, the hydrology. And so if you have, let's say in a dry year, low flow within your river, what we call the base flow or annual minimums, you see that that flow invariably influences the groundwater table adjacent to the river. And this groundwater will typically be beneath your floodplain. And that water table is essential in supporting plants within that landform. But if the flow increases above that annual minima to a point where it's still below the banks or the lowest point along the banks of a river, then the stream power is increased to such a point that it tends to carry along sediments and organic matter downstream. And so as the flow becomes even larger, and larger here means I'm talking about that which has the potential to cause flooding. And in terms of hydrology, this will be something that is above your typical 1 in 2 year event or normal flow, as you would call. So we're talking about, let's say 1 in 5, 1 in 10, 1 in 25, 1 in 100, 500 year or a greater event. When you have such flows happening within your river system, then there are associated geomorphic and ecological processes that are carried out within the river and your floodplain. So in terms of geomorphology, when you have such large flows, you have sediments being carried along onto your landform just adjacent onto it. So you have the sediment and organic particulate substances within your river settling out within the floodplain and becoming, if you will, the substrate or the bed upon which plants, fishes, and all that can survive. And so in terms of hydrology, you have low flow events happening very frequently, like once every 2 years. But for larger flows, you would have, let's say, once every 1 in, let's say, 500 or 200 years, the chance of that happening. So if you have a larger flow in inundating or flooding the land adjacent to it, depending on how long that occurs, you could have ecological activities such as fish getting enough food to eat or habitats where they can survive and populate. Then you can also have various shapes of land being formed. Now, if there is, let's say, a dam or a reservoir upstream of a river and the flow is being regulated, then you have the timing of the flow not the same, and such fluctuations within the flow can influence the reproductive cycles of organisms living in the river and the floodplain, or the establishment of vegetations or ability for the organisms to find food. And depending on that tempo within that change, you can have organisms such as fishes being stranded, or a suitable habitat being created for their survival. And depending on how long the inundated water stays on the floodplain, you could have so many water quality processes also going on. So for instance, you can have settling of nutrients within the floodplain and the transformation of organic matter into various forms occurring at the same time within the floodplain. So all that I've talked about so far are just how the river influences the floodplain. But you can also have the floodplain also influencing the river. So it can store excess water from the river. So you would only have flooding occurring when the carrying capacity of the river is exceeded. So that all that excess water tends to be stored within the floodplain. And when such storage occurs, you have shear stresses within your river, the main stem, being reduced. And what that means is that you have erosion being reduced in the river. So that's a benefit that is gained from the floodplain for the river. Because when the stream's power is enough to carry sediments and all that, you could lose some essential organisms and fish eggs within your main stem, and the population of fishes can be reduced. And within the floodplain, as the river flow recedes and eventually flow on the floodplain also calms, you have depth and velocity decreasing. And as depth and velocity decrease, we have nutrients that are absorbed onto sediment particles settling out. So you have, for instance, nitrogen and phosphorus settling out on the floodplain. And that nitrogen and phosphorus are essential nutrients for plant survival. So that's what helps them to grow, assimilate food for their survival. But the nitrogen and phosphorus from the river also get removed by those plants. And so it's been established within the scientific literature how the floodplain is a hotspot for several biochemical activities. And so it's a well-studied site. And for instance, you can have riparian forest or wetlands serving as filters for nutrient loading. So let's say you have a farm uplands or agricultural area where fertilizers are applied as rainfalls and overland flow occurs and they travel down the hill. The interface between such a system and your river will be the floodplain of forest trees and wetlands, and the forest trees and the wetlands can act as filter to your nutrients coming off from agricultural lands, and therefore the nutrients which would have polluted the river would have been filtered off. So from the foregoing, all that I've been describing so far, I'm trying to paint the picture that the floodplain is a biophysical system. It's not just looking at it from the eyes of hydrologists, which would just be the land just adjacent to a river body. And so in our management, we only focus on the relationship of the flow and that land, but there are also biological processes that are also happening within the floodplain. So their management must take into consideration all those processes. We gain so much from the floodplain. They are source of fishes, drinking water. They serve as filters to remove waste from municipalities. We can even find minerals, gold and other minerals from in the floodplain. And because of the deposit of nutrients, they are very fertile for farming. Then also some people like the sight of water, so they will want to develop their residence close to water bodies. Also, you have industries built in the plain. So there's this huge economic benefit that are gained from the plain. And flooding is the driver of most of these benefits. The same flooding is also seen as a menace within the society. And so, though we are gaining from the floodplain, because of the danger associated with flooding, we've been mitigating it for a long haul. And so in the literature, we see that every year we have over 100 million people being affected by flood disaster. And there's been reported 10,000 fatalities every year. 10,000 is way too much. Even if it were just a person that dies, that is way off the charts. And there are reported damages in terms of infrastructure and or buildings to the tune of $40 million every year. Meanwhile, jurisdictions around the world are also investing heavily in what we call the flood control infrastructures in a way to curb the menace of flood disasters. And we do that through dams and their reservoirs. So what those structures do essentially, they tend to attenuate floods. So they will curb the flood peak, reduces it and dissipate it slowly downstream through their spillways so that they don't cause havoc downstream of a river. You can also have levees alongside your river systems. And what the levees and the flood walls do essentially is to cut off the river flow, the high river flows from inundating the floodplains so that lives can be saved and properties also saved. Then some approaches are also dredging, that is essentially removing sediments and organic from the river system and creating more carrying capacity to accommodate higher flows. So this is what we've been doing for a long time, since 1700s. But we've identified so many issues with such approaches. And one of them is the disconnect between the river and the floodplain. So for instance, if our strategy for mitigating flood is to put up berms or levees or dikes, then essentially what we are doing is in a barrier between the communication of a river and its floodplain, like I've demonstrated in the previous slides. And so we prevent inundation happening or we put up this dam and reservoir structures, which in the end regulate flow, timing, and frequency. And the unintended consequence of that is loss in ecosystem services, including fisheries, biodiversity, and introduction of invasive within the floodplain. And so there is ample evidence within the scientific literature of a change in paradigm of how the system is managed. And so one way to do that is through looking at the system from different angles, not just through the eyes of hydrologists or civil engineers, but putting on geomorphic lens and also ecologists. And so ways to do that is through approaches such as protecting the plain, restoration, or reconciliation. And so in terms of protecting the floodplain, we can do that through policy arm of municipalities or jurisdictions. And so what this means is that we zone development. We do not allow development to happen just anyhow or any ways within our countries, but we establish policies. Those policies become the platform or the bedrock of development. So nobody builds without having a permit, and within that permit there are checks. A number of things would have to be checked before finally you have the axe hitting the ground. And so such an approach, the zoning approach, has been going on in Europe and North America extensively. And another way to look at it is restoring the floodplain through connecting the breakage between your river and the floodplain. So with such a strategy, you can have, let's say, a levee, the elevation of a levee being lowered. So you would have flow passing over that to the floodplain, or manage vegetation within that floodplain, or increasing flows. Dam releases what we call in-stream flow. You increase that so that there is enough water to flood the plain during certain seasons. And so we will go through two of these approaches in a little length: the zoning and how flows can be augmented to support species habitats within the floodplain. And so for the zoning, once a regulatory flood policy is established, we have what we call the two-zone policy area. And with such a policy, the floodplain is divided into two zones, one being the floodway and the other being the flood fringe. So once a design flood is selected in the policy, 100-year flood or 500-year flood, we delineate that zone. And in the floodway, you have the stretch within your floodplain that is the most hazardous, in a sense that is the zone where the flood water is deepest and fastest. And that combination of depth and velocity generates enough stream power to cause havoc. So you can have a person's feet being stripped off with such force when the flood event happens in such a zone. And because it's such hazardous, development within that zone is typically restricted. And beyond that zone within the floodplain, we allowed development, but with the caveat that such development or houses or in industries ought to be flood-proofed. What that means is that you don't just develop right off the ground, but you kind of elevate a bit above the ground with structures and before you build, such that in the event of flood, a house is not flooded. So this is a typical example of a two-zone policy where you have the floodway delineated and the fringe where developments can happen. So once the water rises above the bank, it's able to inundate the floodplain for those ecosystem processes to still go on. Meanwhile, on a certain distance from the main river bank, we can still build our houses and enjoy all the other economic activity. So this approach is not totally limiting the traditional means of development, but once we add this additional lens, we are able to sustainably carry out development. And so a typical workflow for achieving such delineation is to start off with data collection, collecting data about the topography, the river, and the flow of the river. And once that is done, you can estimate your design flow, and together with information carried out on the topography, the channel cross sections, hydraulic structures within your floodplain, covers, bridges, dams, the kind of land cover within the floodplain and the river, then we can carry out hydraulic routes. And so we can do that numerically, not just solving it on paper, but approximating conservation of mass, momentum, and energy with mathematical equations in a form of a model. When that model is just looking at it in one direction, what is called the 1D models, then we can use solvers such as the standard step approach, which only solves the equation in just one direction. But if we are interested in two-dimensional way of looking at the floodplain, which is more realistic, then the shallow water equation is approximated with a number of schemes. And so once the hydraulic model is set up, we have to make sure that it's able to mimic historical flooding events in the hindsight, and also validate with a different set of observation. Then we estimate any form of errors within the model with uncertainty or sensitivity analysis. The output of such model will be flow depth or flood elevation and velocity. And with this output, we can delineate the floodplain in terms of the floodway and the fringe. And with such a map called the flood hazard map, that can be incorporated into a zoning bylaw where municipalities developments are carried out according to that law. So to do this, terms of the hydrology, we need that design flow. So the design flow will be a flood that is selected by the municipality or a jurisdiction as to what they are comfortable in handling. Of course, we can't handle every flood, but we have to be comfortable enough to say that based on the economies of the society, we are comfortable with this level of flood. So that becomes our design flood or regulatory flood. And once that flood is selected, then if we have historical gauges or stream flow records within our catchment, then we will be interested in what we call the instantaneous flows. That is an annual maximum series for a long period of time. Typically, we are looking at somewhere in the neighborhoods of 30 years for the analysis to be statistically relevant. And so with that data set, we can fit a frequency distribution to the annual maximum series, then come up with our design events that ought to be routed through our hydraulic system. There are so many numerical tools out there that can be used in delineating the flood, and one of them is the HEC RAS or HEC RAS that is used predominantly in the industry. There are also tools like 2Flow, Mike 21, Mike Flood that can also be used. So typically what is done is to set up a computation mesh to solve the shallow water equation as the design flow is being routed through our study area. And once that event is solved throughout your study area, the result of that is an inundation map where we can easily see where velocities are very high and also the extent of the flood beyond the banks of the river. And so with such a result, we can easily, with some post-processing in GIS, delineate the extent of the flood and separate them into the two zones, floodway and flood fringe. So this is an example of such a map where the deep blue area is your floodway and the light blue area your fringe. So the floodway, like I mentioned before, would be where we wouldn't allow any development because it's very dangerous to have like a house or a person in that zone once that event happens. And so development is restricted. But beyond that, in this light blue area, development can happen with flood proofing. And so that is it for a means of protecting the floodplain. Another way that we can adopt is in-stream flow analysis or regulating how dams release flow downstream so that there will be enough for ecosystem processes and the survival of fishes mainly. So with such an approach, again, we go out there and collect some information with respect to the conducive environment for fishes in terms of their life cycle. So throughout the stages of life of a fish, we are interested in what hydraulic conditions are suitable for their survival. And this, when I talk about the hydraulic conditions, I'm talking about flow depth and velocity. What flow depth and velocity within the floodplain will be suitable for, let's say, the egg of a fish throughout when when they grow to become adults. And with such information, we develop what we call the habitat suitability curves. And once we have what the fish prefer in terms of those hydraulics, then we can model our steady river or stream and calibrate the model, validate it, and generate similar velocity and depth. And so we combine the two to what we call hydraulic suitability index and create map to show locations alongside our river body where fishes can survive and at hot flow rate. And so once that is done, we come up with a map to locate all those areas and also speak to our dam operators as to what flows can be released at what time during the seasons that can help create habitat for the survival of fishes. So this is an example of the habitat suitability curves for both depth and velocity. And what this is saying that up until, let's say, 0.5 meters depth, you would have the optimum condition that the fish can survive. And as you go above that, that will be too much for them. So the habitat that is created becomes unsuitable for their survival. So with this information, you can inform like an operator of a dam or a reservoir system as to how much flow can be released downstream to ensure that this condition in terms of depth and velocity are being met. And so we can also create a 2D model to show where areas within the floodplain where the suitability can be achieved and where fishes are located, and the need for us to also preserve such a location, or if they are degraded, restore them back to, if possible, their original state to enhance the reproduction of fishes. And so in summary, what I've been trying to convey all this while is that the floodplain is complex. It's not just a hydrological system, but a combination of hydrology, geomorphology, and ecology. And the traditional way of using just structures, hydraulic structures to control flood in terms of attenuating the flood and mitigating it has not been too successful because of unintended consequences. And so there's a need to combine both the structural approach and the non-structural approach in the management of the floodplain. And with that, I come to the end of the presentation, and I'll be happy to take any questions. Thank you very much.
Thank you very much, Dr. Eric. Please, if you have any question, you can raise your hand and ask, or you can type it in the chat box. For the meantime, I would like to know when it comes to flooding in Ghana in particular, you know, the Wager Dam, every year we hear of news about the dam spillage. Every year they release water from the dam and it affects residents downstream. Are there no any sustainable way of using such situation instead of spilling the water?
Okay, yeah, that's a good question. So invariably, so that's the kind of message I've been, trying to present, in the sense that releasing downstream flow can be done sustainably, right? But invariably, we don't have to wait until an event hits before releasing the flow downstream to go and hit people downstream, right? So, but if we have a system of coupling hydrologic forecasting with the management of the reservoir and the dam, then we will know way ahead of time when such an event will be happening, right? So let's say there is a forecast of rainfall, let's say 7 days or 10 days ahead of time, that there is this huge event that will be happening in the next 10 days. That is one part. So once that forecast, a system of coupled precipitation, rainfall runoff, and reservoir routing models in a place, then we can simulate the event right ahead of, like before even the event hits, and know how we can strategically release flow downstream to prevent the flooding. So it's a systemic issue of not having a forecasting system, a reservoir management plan. And such a plan would have had in its protocols ahead of time how to manage the system during flood with information from a forecast, right? So you wouldn't have a situation where we are flooding, let's say, people downstream every year. That is way too frequent. If there's a plan in place of how the system is operated and there's a forecasting system and that is being simulated, we will know way ahead of time that such an event is coming. And even if we cannot manage it with the capacity of the reservoir, we will give enough warning ahead of time and relocate residents downstream so that nobody is caught up within the flood. Does that answer your question?
Sure.
Okay. And one thing I want to add is that all that I've talked about can just remain on the shelf, even if we enact policies and we don't implement them. Like I know about Ghana, we have so many policies, but the issue is implementation. If we don't implement them, they mean nothing, right? Yeah, so I mean, apart from what I also talked about, there are also several ways that we can also mitigate that, right? And one of them through natural floodplain management. So apart from what I've talked about, it's one of a system thing, but also we can divert, you know, if you look at along the course of the river, you can divert some of the flow that eventually ends up. So because I can, from what you are describing, it's also an issue of the capacity of the reservoir not being able to accommodate, you know, the inflow into it, right? So way upstream of the river, we can also reduce how much ultimately gets into the reservoir by diverting some of the flow upstream of it into like an area, let's say a flat plain with a berm that can store some of the flow during the event up until a certain time, like through detention and retention. And eventually, when the event calms down, we can slowly release the water back into the system. But all this thing can only happen with simulating and knowing ahead of time the event that would come. We can only do this through modeling, like simulating the event ahead of time and also trying mitigative solutions. And one of them is what I've talked about. You can divert flow from the river into the floodplain and store that amount of water for a period of time through retention and detention ponds. Then once the rainy season passes, then you can slowly release the water also back to the river. So it's a lot of planning must go into it, and a lot of systems also must be put in place to do that. Otherwise, then those yearly flooding will happen. Yeah.